Wes will talk about exploring the impact of system storage on AI and ML workloads, and he's going to do some interesting MLPerf benchmarking and analysis. Wes is with Micron Technology, and before Micron, he's also had some experience working at Dell. So with that, Wes is on.
Thank you. Hey everyone, I'm Wes Vasky. I'm a Principal Solutions Engineer at Micron, and I do application performance testing for our storage business unit. And for the last year or so, I've been analyzing the performance of AI, ML applications, primarily through the MLPerf benchmark suite. And I'm going to present some of those results here for you today. So the first question that I needed to answer when I started doing this testing is, does system memory and storage actually have an impact on the performance of the AI training workloads that I was going to be looking at? So to test that, what I did was artificially constrain the system that I was using. So I have an 8 GPU server, have a ton of memory in it, 8 NVMe drives, and I run the model on it, training ResNet 50 off of ImageNet. And then I limit the amount of memory to 128 gigs. That's enough that the model can train without any issues, but the data set is not going to fit in the file system cache. So that every time you hit an XDPOC, you're going to be reading from disk. I also limited the disk throughput to 500 megabytes a second. That's going to correspond to a virtual disk that you would get if you were doing a cloud VM with 8 GPUs attached to it, and you didn't realize that you needed to start striping across multiple. And what we see is that for a poorly architected system, you can just trash the performance of your training. And you're going to need at least a high amount of memory or fast enough drives, and ideally what you want are fast storage for your training data set and enough memory to fit that entire data set. Reminder, I work for Micron, we do make memory, so if you do want to fit your whole data set, we'll help you with that. For the most part though, that's impractical. Okay, so now we know that that can be an issue. You do actually have to architect things properly. So what am I going to do? I'm going to talk about MLPerf. I'm going to figure out what system resources are actually being utilized for training a few of these different models. One of the questions that we get is whether or not SATA SSDs are fast enough. And then I'm going to look at a little bit more complicated use case that is going to make sense once we go through those first three. I do have a handful of context slides that I'm going to go through real quickly. So if you are planning on taking pictures, I apologize in advance. I'm going to make it difficult for you. MLPerf overview on the training part. So as of right now, MLPerf is a benchmark suite that is under very active development. Version 0.5 had their first submissions released in December of last year. Version 0.6 was about a month ago. It's very rapid development, and we're seeing a lot of interesting things happening. I am running these tests, and that's the data that I'm going to be showing you. For inference, that is undergoing the first submission process now. So I'm not going to have any inference data from these currently. That submission process should be finished in September. We should have data in October. I will start looking at the same results and publishing that on our website for you. All of the data that I'm going to be going over was run on the exact same box. It's a Supermicro 8 GPU system. It has two top-end Intel Purley CPUs, 28 cores, 2.5 gigahertz. I've got a boatload of memory in there, mostly because we make it and I had it available. Each of the GPUs has 32 gigs of memory. This configuration is going to be very, very similar to an NVIDIA DGX1. It is the same GPUs with the same memory, the same interconnect between the GPUs. The difference is going to be the CPUs that I used and the storage that I attached to it. I look at an 8 SATA configuration and an 8 NVMe configuration, each of which is going to be RAID 10. So this is really going to be kind of the most trivial use case you can see. I'm using local storage with a bunch of GPUs to analyze what's actually happening. A lot of these results are going to inform what you would do for larger distributed architectures, but I wanted to maintain a simple to test and understand architecture. So I say it's similar to a DGX1. How similar is it? If I run the code that NVIDIA submitted as part of their MLPerf version 0.5 submission, I get the same results. So this shows that for the application workload, we are bottlenecked at GPU compute performance. I have the same GPUs, run the same test, we get the same results. So what resources on the system are these benchmarks actually using when we're running them? So this is going to show the GPUs. GPU utilization is relatively high. That shows that for the most part, training these models is a well-optimized process. We've got good CUDA, good drivers, good frameworks, and we have high utilization there. The memory utilization numbers here are going to look a little strange. It looks like we're really not doing the most to optimize the performance, so we could probably increase batch sizes to increase our training throughput. Unfortunately, because of the small size of the data sets available for benchmarks, the low memory utilization is more of an artifact of that. By increasing the batch size, the batch would become too large of a percentage of the total data, and it would decrease the overall training throughput. With real-life workloads, we would expect to see significantly higher memory utilization, and for other tests that we've seen, I have been able to corroborate that. PCIe bandwidth, just to show that it's not a limiting factor. Average across 8 GPUs is about 3.2 gigabytes a second. Times that by 8, we're about 26 gigabytes a second. So the equivalent of about 2 16x PCIe slots, and we actually have 4 connections from the CPUs to the PCIe switches that the GPUs are able to use. CPU utilization. So I did this non-normalized so you can kind of see what your system CPUs need to be, 3,200%. So if you're looking at 32 fully loaded cores, 64 half-loaded cores, these are very parallel processes. They scale very well. This is not a significant hurdle for architecting a system, especially after yesterday's announcement where you can throw 128 cores in a 2-socket system. Disk. This is what we're here for. This is why I went so fast through the first part. So when we run these benchmarks and we just measure the average disk throughput, we get some really strange results. We're at about 12 megabytes a second. You're probably asking yourself, why are we even talking about this? I can throw a SD card in a system and hit 12 megabytes a second. And this is, again, an artifact of doing the benchmarks. The data sets for these benchmarks are relatively small. The largest data set that I have access to for these benchmarks is ImageNet, which is still under 150 gigs. 150 gigs is very easy to fit in memory. All of the data sets together for these benchmarks are less than 400 gigs. And when we talk to customers and we talk to the data scientists inside Micron who are actually running AI, we know that that's not a realistic environment. Real training workloads are going to be in the terabytes to petabyte range. They do not fit in memory unless you have unlimitedly deep pockets. So what can we do so that we can run these benchmarks in a way that is going to be more representative of what customers are actually seeing? And I touched on this at the beginning. I used the Docker container memory resource limits to constrain each of these benchmarks to enough memory that they have no problem running at full performance. However, the data set is not going to fit in the file system cache. This ensures that for each epoch, when we have to read through the data set again, we are reading that from disk in the way that real customers are actually seeing with their real workloads. And as you can see here, the performance for a memory-limited environment to a non-memory limited environment are identical application performance. Okay, so we can do that and get the same performance, but what does it do to disk? It does exactly what I was setting out to. I can get my disk throughput significantly high for running these sorts of benchmarks, and for image classification, we'll see the highest disk throughput for any of these. The average is showing at about 1.1, the peak is about 1.2, and the peak is hit very consistently. Single-stage detector is about half that, sitting at about 500, 600 megabytes a second. That, on the surface, doesn't seem very hard to architect for. And object detection actually seems almost negligible. We're at around 50 megabytes a second, average disk throughput for training the object detection benchmark. And if we look at the image classification, we're 61 times higher. That makes sense with 62 epochs. Originally, we were only reading data from disk during the first. After changing this, we were reading for all 62 epochs. Therefore, 61 times higher. Okay, so the first question, is SATA fast enough? If you are doing an isolated benchmark with a single server, local drives, all of your data fits in the system, and all you're doing is training, SATA drives are going to be fast enough. In this instance, I'm actually able to get full performance out of just 3 SATA drives with the data stripes. Now the problem with that is that's not really representative of real environments. People don't have an isolated system that is just running a training workload and the disks are remaining idle otherwise. What we see after talking to our data scientists inside Micron and talking to customers is that it's a more complicated environment. If you have a single server that's going to be training models, that server is going to be reading from some sort of cache system where you store your data. In this case, I'm representing that with my internal NVMe drives. Well, as you are loading data sets for the different models that you need to train, you're going to be running that sequentially. And after the first data set loads into the system, you'll start training your model on that data set. And at the same time, the data for the next data set is still going to be ingesting. So even though this looks like a very read-centric workload, and for the most part it is a mixed workload at the end of the day, because whatever cache system you're using to actually hold your data sets has to get data in and out of it so that you can actually use it. So to represent that, I did a 32-job FIO run. Each one was just a queue depth of 1, writing to 32 different files, XFS. Each was a very large file, large transfer size, a relatively optimized way of ingesting data into a system. And the first thing that I wanted to know is how different is the ingest rate for NVMe versus SATA drives. And here the difference is stark. NVMe can ingest on these 8 drives in RAID 10 at 10 to 12 gigabytes per second, whereas SATA is limited to about 500 megabytes a second. That's a pretty large difference. The next question is there an impact on the application training performance? And here we see that image classification has no impact. When I first set out to do this testing, that was the benchmark I thought was going to show a difference, and that's because image classification showed the highest disk throughput. Object detection, if you remember, had an almost negligible disk throughput. We were just a few tens of megabytes a second. However, when we run this with a simultaneous ingest, we see that on NVMe, there's actually a small performance regression on the order of 5 to 7%. The single stage detector benchmark, which was sitting around 500 megabytes a second of disk throughput, sees about a 30% performance reduction in training performance if you're running a mixed workload on your storage at the same time. Again, this is not what I was expecting when I set out. I was expecting the benchmark that is the most storage intensive to be the most dependent on the quality of your storage performance. That is not the case. So I have not had time to find out why NVMe had a performance regression on object detection and SATA did not. I'm inclined to think that it's due to the architecture that I'm using, where the NVMe drives are not on the same I/O root complex as the GPUs on the PCIe switches and just the architecture there. I'm going to be doing future work to examine that further, but the first step is to understand, can we at least mitigate the impact of this? Now, on object detection, if we limit the ingest rate and increase the block size of transfers, we can wholly mitigate the impact of doing that ingest at the same time. And I did the same thing with the single stage detector on the SATA drives, and again, the story is the same. Here, we didn't even need to limit the rate. All we had to do was increase the block size from 128 to 1 meg, do a more optimized version of this ingest, and the impacts are mitigated. So at the end of this, I'd love to say, here's how you should architect your system. However, as I was running my test on MLPerf version 0.5, 0.6 came out with results about a month ago. And what we're seeing is that the time to train these models has already decreased 15 to 35% in 7 months. And not only is the training time decreasing, for most of these benchmarks, the accuracy target has actually increased. So not only are we taking less time to train the model, we're training the model to a higher accuracy threshold. This is making it very difficult to try and architect systems and know that it's going to be able to handle the workloads that you need. Our recommendations are going to be NVMe systems, especially because it's going to be mixed use cases, and enough overhead and limits on your ingest and your non-prioritized workloads such that you're not going to be impacting the performance of your model training. If you have questions, we'll go to those now. Take a picture of this one, it has my contact information. The slides are uploaded. We'll be able to get it on the Flash Memory Summit website. If not, or if you need it sooner, feel free to reach out to me. I will refollow on Twitter and I'll connect to anyone on LinkedIn. I have a few blog posts where I actually dig into a little bit of this data a little bit more deeply. Feel free to go ahead and read those. Thank you very much.
So we're open for questions for us, please. When you ask your question, please identify yourself and affiliation.
Sure. My name is Shirish. I'm a firmware engineer at Intel. First of all, thanks for the presentation. My question is, when you don't see the difference between the NVMe and SATA, do you have any insight on what was the limiting factor that was not improving the performance with the NVMe?
Yeah, so when we're looking at NVMe versus SATA and the performance is looking the same, this one, right?
Yep.
We're compute limited. So if we go back and look at the GPU performance here. So for the most part, the GPU utilization being the lowest here, 68%, that's very high. So at that point, it's needing to be optimizations for getting better use of the compute resources to get that up into the 90s. And on image classification, where we're at 93% GPU utilization, it's very unlikely that anything else in the system is going to be able to improve the performance. So that's why most of the work that I was doing here was finding out what are the things you need to avoid such that you don't hurt your performance.
Right, because I think one thing I was confused because your GPU utilization is lower, but you don't see the performance difference.
Yeah, and for the most part, I think that's going to be down to specific architectural issues. So whether or not, let's say, the tensor cores in the V100s are being utilized for different layers, and whether or not it's limited just by the memory bandwidth and latency on the GPUs themselves. That's not something that I have tested in this case. It is something that I'll be testing moving forward, and the guys on the memory side of Micron are also working on that, measuring the impact of improving memory throughput. For some of these, I already know that it is going to be memory limited for memory on the accelerators.
Okay, thank you.
Yep.
Hi, Manoj. Quick question, I think somewhere there. When you split from memory to SSD, what kind of impact did it have on the training time?
Yeah. So depending on the storage subsystem, if we limit memory so that it has to spill to disk, there's not an impact on running time. That's what this is showing, is the actual runtime of the training application. So this is the time to train a model to the specific accuracy. This is the benchmark result that you get out of MLPerf. And so long as I had fast enough storage, it was not going to impact things. The first slide that I showed with a chart on it, this was a kind of a contrived use case where I'm limiting the storage throughput to 500 megabytes a second, because that is the same as what you would get from like a virtual disk through a cloud provider. However, 500 megabytes a second is less than a single SATA SSD can do. So as soon as we're looking at this, if we throw 3 drives in there, we have enough throughput to meet the minimum for training a model.
Thank you for a great presentation. Yelena from Engineer. Question regarding the preconditioning the drive. Is there any, before starting those tests, is there any...
Great question. Yeah, so the way that I run these tests is I don't precondition and keep it full because that's not a realistic use case. People don't do that. I do put enough random data on the drive such that it's 80% full. So we're running in a relatively high usage environment. And then I'm writing about a terabyte of data over and over. So I keep the drive full such that we're in not the absolute worst case, but we are trying to be representative of a bad use case. Does that make sense?
Yes, definitely. And the second question, my assumption was this is on a Linux system, OS.
Sorry, what?
The tests were run on the Linux system.
Yes, this is Ubuntu 18.04.
Have you ever maybe have any data from other OS like Windows? Or
Not at this time. Is that interesting to you?
Very.
Right, you said Microsoft, right?
Yes.
Okay. It's on my roadmap. I'm one person right now, but I will take that as advice. Thank you.
Let's thank Wes again for a pretty nice talk.